My name is Pete DelVecchio. I'm the product manager for the Tomahawk switch family at Broadcom. And we'll have 3 presentations today on 3 chips we announced over the last few months. I'll start us off with Tomahawk 6. Robin Grindley will cover Tomahawk Ultra. And Henry Wu will take us home with Jericho 4. So to first set the context, make sure everyone is familiar with all the terminology we'll be using. Just want to make sure people are familiar with what's known as like scale up, scale out, and sometimes being referred to also as scale across networking. So scale up networking today is usually within one rack. I mean, it used to be like one box with 4 to 8 GPUs. Today it scales to one rack. We see in the future that that scale up domain will be increasing significantly. We see customers asking for scale up connectivity up to maybe 1,000 or more XPUs. But current state of the art is currently one rack. Scale out would be connecting those scale up racks together. So you could have scale out within the data center, so across racks, and then what's referred to as scale out or scale across between different data centers. So we have custom chips that are designed for these specific applications. So the way these different chips that we announced over the last few months fit in is that we have Tomahawk Ultra. Now this focuses on high-performance computing and AI scale-up. Tomahawk 6 that I'll be going into on depth focuses on AI scale-up and also scale-out. And then Jericho 4 would be bridging scale-out and scale-across. One of the reasons that these span different domains is that you see that it's not one-size-fits-all. That different hyperscalers, different type of XPUs, different workloads, they have different architectures, different communication patterns. And also AI training and inference has different needs for the network. And because of that, we do allow flexible deployments. We have, say, Tomahawk Ultra. So on the bottom left there, you see Tomahawk Ultra and Tomahawk 6 could be used for scale up. Once you get to scale out, as mentioned before, that could be Tomahawk 6, or depending on the endpoints, the traffic patterns, it could be a Jericho 4 that you see on the right-hand side. And then Jericho 4 would be something that this will allow the connectivity between data centers and potentially between regions for larger scale-out clusters.
So, I mean, Jericho 4 doesn't have the bandwidth of the Tomahawk 6. Mm-hmm. So you could see that. You want to go back to the prior slide? I'm sorry.
Sure.
That the Tomahawk 6 would be piped into the Jericho 4. I mean, I'm trying to understand how it would work.
Yeah, so normally what you'd have is within a building, generally you want to have a wide and flat cluster. So most companies, most customers don't want to go to more than 2 tiers in the network within a building. So you'd have that 2-tier network within the buildings, and then you'd have something connecting those 2-tier clusters together using a Jericho 4.
Okay.
Yeah, if you go, and I'll get into this some more on Tomahawk 6, but there are a lot of benefits in keeping that cluster as wide and flat as possible. If you go to multiple tiers, it really makes the congestion control, the load balancing a lot more difficult. And you also wind up with a lot more switches, a lot more connectivity between the tiers. So I did want to mention before getting into Tomahawk 6 that we do have with Broadcom a full stack of AI products. So provides switches, so Tomahawk Ultra, Tomahawk 6, Jericho. We have the endpoints, so we have NICs. Broadcom is well known that we do a lot of custom XPUs. So for our customers that are doing custom XPUs, we can provide NIC chiplets. So they would focus on the processing elements. We could do all the networking. They could instantiate either as some IP on their chip or as a full chiplet. And then if a customer wants to roll their own IP, their own Ethernet connectivity, we provide a framework, specifications for how you can use Ethernet efficiently for scale up. We have physical layer products. So we have retimers, we have DSPs for optical modules, and we have optics. So we have co-packaged optics, we have multi-mode and single-mode optics. Now on the CPO side, we've announced that for Tomahawk 6, this will have a CPO version. We've actually been doing co-packaged optics since Tomahawk 4. And I think the first thing I'll pass around is for show and tell here. So this, if you're interested what something with CPO looks like, so this is a Tomahawk 5 with co-packaged optics. So this is shipping to multiple hyperscalers. There'll be some very interesting results that some hyperscalers will present at ECOC later this month. But this is basically the Tomahawk 5. the same die that we use for the electrically connected version with co-packaged optics included in the same package. So I'll pass that around in case anyone wants to take a look at that.
I want to go back. You said XPU. I didn't catch that.
Yeah, so basically, so GPU is kind of a relic of people using, a graphics processing unit for AI training or inference. So XPU is just kind of a generic term saying
like star.
Yeah, it's kind of like a star. Yeah,
PU.
Exactly.
Okay.
Yeah, exactly.
FPU, NPU, LPU, GPU, CPU,
TPU.
Yeah. Star.
Mm-hmm.
No, I'm not the star.
Thanks.
So wildcard P.
Okay, gotcha.
Okay, so getting into Tomahawk 6. So this is a follow-on to Tomahawk 5. Tomahawk 5 is very widely deployed in hyperscale scale-out networks. This is actually the chip that really drove the transition from InfiniBand to Ethernet for AI scale-out. And if you went back a few years, what you saw, there's a debate about that for the scale-out networks, do you use InfiniBand or is it Ethernet? It's pretty much a given that for the general data center networks, the wider network is going to be Ethernet. But the narrative a few years back is that to get the highest performance, it's got to be InfiniBand. Right. What you've seen over the last couple of years is that's completely transitioned. I think there's one hyperscaler that's announced they have large clusters with InfiniBand. Everything else is on Ethernet at this point. So that debate about scale out is over. It's clearly Ethernet at this point. As we'll get into, there's a debate about, okay, what do you do for scale up, that last hop, that last part of the network? We also feel that Ethernet is the appropriate choice there. So, Tomahawk 5 has proven itself in the largest GPU clusters. This is the only monolithic 51.2T chip on the market, so it's really the most efficient as far as power, as far as latency, fixed performance, and this is widely deployed throughout the world for GPU clusters. Tomahawk 6 steps this up in every dimension. So, we have double the bandwidth, double the SERDES speed. We also add a lot of features that will improve the efficiency of these networks, reflecting the different endpoints and the different workloads you have for AI. So Tomahawk 6 is not just about speeds and doubling the bandwidth. It's also about adding a lot of efficiency for load balancing, congestion control. Okay, so getting into scale up and scale out, as I mentioned before, there is this discussion about what do you use for scale up networking. We're seeing a lot of traction for Ethernet. A couple of the reasons is that it's an open ecosystem, a lot of suppliers for Ethernet. One thing that's probably not obvious too is that a lot of these hyperscalers, they have these very large clusters that they can partition between different customers. So, if they have 100,000 GPUs, one customer coming to them is probably not going to rent that whole cluster. So they might want to partition that differently. So if they have Ethernet for a common interface between scale up and scale out, they can actually partition that cluster differently for different workloads and really what a customer wants to rent from them. Another big benefit is using Ethernet here, you have a common technology stack. So the same debug tools, the same networking tools, the same optics, DAC connectivity, you can use that for scale up and also scale out.
On an earlier slide, you mentioned Tomahawk 6 was also used for HPC. Where do you see that?
So that would be Tomahawk Ultra. So Tomahawk Ultra, so Robin will get into that, but yeah, the initial design point for Tomahawk Ultra was HPC, and then we saw later on that scale-up connectivity was becoming more important. We actually added some features to that, so it's appropriate for HPC and scale-up, but Robin will go into that in depth.
That's sort of a different Ethernet, networking profile for HPC. Okay.
Yeah, definitely. Yeah, and Robin will get into like some of the exact characteristics, what's different from, say, scale-up, or general scale-out or data center networks versus HPC.
Where does Ultra Ethernet fit in all this?
Well, actually, it's right here. So, Ultra Ethernet was formed about a little bit over 3 years ago now. And the purview of Ultra Ethernet is to advance Ethernet for all of HPC and all of AI networking. So the 1.0 spec is known to focus on scale-out. But there are some technologies there that are also applicable to scale up. So this kind of gets into this slide here that, this is the way we see the Ethernet, scale up landscape is that a lot of folks want to use the Ethernet PHY, they want to use the Ethernet data link layer, but they want to have some innovation above that. So we had earlier this year announced SU, so scale up Ethernet, and that is one thing that you could have as like an upper layer or a complete framework for using Ethernet for scale up. We see a lot of hyperscalers, a lot of customers want to be able to innovate at that transaction layer or that the layers above the data link layer. So we provide SU as an example. We do see that, it's been announced that some companies are looking at doing, say, UA link over Ethernet. And some other people want to have their own custom accelerator implementations over Ethernet. So as far as Ultra Ethernet, what we show is that in the context of scale up, that we can leverage a couple of the features, in particular LLR, so that's link layer retry, and CBFC, credit-based flow control. Those were standardized in the 1.0 spec, and those can also be used for scale up. So all of our switches are Ultra Ethernet compliant, and then depending on what features you want to leverage from that spec, you can pull those out or just use that for your network. You don't have to use all the features. For example, LLR, CBFC are optional, depending on what sort of congestion control, how you want to manage the link layer.
I thought Ultra Ethernet had some application-specific functionality as well. If you were doing AI training versus scientific analysis of.
Well, there are 3 different profiles in Ultra Ethernet. There's an HPC profile, there's an AI base, and an AI full. So yeah, depending on if it's HPC, there's going to be a subset of the functionality.
Is that at the data link level only, or is
no? The thing is, so Ultra Ethernet is actually kind of a full stack. It's pretty expansive. So it's got all the way from link layer, it's got PHY layer, link layer, it's got transport, it's got software. So there's some, there are like 4 horizontal working groups. We got PHY layer, link layer, transport, and software. Then we have some vertical working groups that try to integrate those and show for certain applications like storage. We'll say storage, this is how you apply that, drawing from the different layers.
Okay.
So yeah, Ultra Ethernet, it is pretty important. We were one of the founders of Ultra Ethernet, and we got 130 plus member companies, so they're like 4,000 contributors right now. So it really is kind of a driving force for AI.
Yeah, at the switch layer, there aren't a whole lot of changes. You need to add things to your switches to make sure that they're not going to block Ultra Ethernet protocols. But at a switch layer, at link layer, there isn't a whole lot of changes to Ultra Ethernet.
Yeah, and a lot of it's optional too. So basically, there are a few features within Ultra Ethernet. So for example, it's got to be Ethernet. The way you do ECN marking, there's just a handful of things. If you say that if you're Ultra Ethernet compliant, here are the things you need to have. But then there are a bunch of optional features depending on, is it HPC, what type of AI workload you have.
Right.
So Robin will get into this. So he'll get into some more about just this framework for Ethernet for scale up, and also talk some more about SU or scale up Ethernet.
And then just while you have a pause here, going back to this chip we've been passing around, what is this?
So that is Tomahawk 5 Bailey.
Okay.
So Tomahawk 5, with that 5 nanometer generation of products we started, we made the SERDES really flexible, that you can connect it directly to DAC, so passive copper. You could have chipped modules, you could have retimed optics, and it can drive co-packaged optics directly.
Yeah.
So that silicon is in the middle is the exact silicon that we shipped originally for Tomahawk 5 for the electrically connected version, and then we put optical engines around the periphery.
Yeah.
So this is basically all the optics aside from the laser. So the laser is going to be external. You have that on the front panel. But this is the rest of the optics you would need for a full 51.2T system.
Yeah, cool. There's a switch in my hand.
Yep. Yeah. Switch with the optics.
Switching a chip. And Bailey is a B-A, how's that? B-A-I-L-E-Y? Is that for somebody's name, or is it a cartoon?
It's a B-A-I-L-L-Y.
Okay, of course.
Yeah. Yeah, so what you'll see is that, so there was so each of the generations, so you see, for example, this is TH5 Bailey will have a Tomahawk 6 Davison, and Davison is an optical engine. It's so named because we have these optical engines, and they can be applied to multiple products. So TH5 Bailey has the Bailey optical engine on it. TH6 Davison will have the Davison optical engine, but that same optical engine could be used by, for example, if someone has an XPU they're doing with our custom ASICs division, they can have that same optic embedded on their chip. Okay, let's see. Maybe I'll speed this up a little bit in the interest of time. So just on the scale-up side, one way to look at this is that scale-up is, in general, you can look at it as like memory sharing, that you're going to be taking some of the bandwidths on an XPU today. Next generation, they might have up to like 8 HBM stacks, so up to 100 terabits per second of bandwidth to the HBMs. So really, between 8 XPUs, you're doing some sharing. You're doing some memory coherency, memory transactions. So you could look at what you have for scale-up bandwidth being a portion of that bandwidth. So today, what you'll see is that companies are talking about maybe 10 terabits per second for one XPU for the scale-up bandwidth. There was one hyperscaler at OFC earlier this year that said, in quote, the next few years, per XPU, they want to see 50 to 100 terabits per second of scale-up bandwidth. So 50 to 100 terabits coming out of one chip just for the scale-up interface. So, 100 terabits per second for a Tomahawk 6 might seem like a lot, but we could throw an infinite amount of bandwidth at AI and it would be consumed immediately. And getting to that point, where you see it today is that XPUs, you might have like 10K XPUs per cluster. It's kind of well known where people are getting to like that 100K level, moving to 1 million plus XPUs in one scale out cluster. If you look at the bandwidth, scale up today is about 10 terabits. As discussed, that's moving to 50 to 100 terabits per second per XPU. And then scale out, typically about 800 gig now, going to 1.6T plus. So if you look at where things are going, we're talking about 100 million terabits per second total bandwidth within an AI cluster. So as mentioned before, one chip, 100 terabits, seems like a lot, but we're just seeing that bandwidth being consumed immediately. I mean, literally, if we had an infinite amount of bandwidth, it would be consumed. Okay, so getting into Tomahawk 6. So as mentioned before, world's first 102 terabit per second switch chip. This is double the bandwidth of any other Ethernet switch chip. Can be used for scale up, scale out, and scale out to more than 100 million XPUs. We do have two versions of Tomahawk 6. So this is one thing I think surprised a lot of folks is that people were expecting that we would go to a 200 gig SERDES with 512 lanes. Tomahawk 4 was the first switch chip on the market that kind of broke the barrier going from 256 to 512 lanes. And Tomahawk 6, we have a version that's got 1,000 lanes. So this is, I'll pass this around. So this is a Tomahawk 6 with 512 by 200 gig SERDES. And this is a Tomahawk 6 with 100 gig SERDES. So this size package, this size chip has basically never been seen before because this is the first chip on the market that has more than this 512 interface. There's actually 1,024 100 gig SERDES coming out of this chip. What you'll see is that it's a multi-chip implementation or multi-die implementation. So the central core has all the packet processing, it has all the traffic management, and there are chiplets around it that provide the different I/O, either 100 gig or 200 gig. So what's interesting about that is that we have some customers that today with their XPUs, with their optics, they're currently running at 100 gig PAM4. They know they're going to upgrade to 200 gig PAM4 at some point in the future. So it's the exact same software, the exact same SDK that you would use for these two chips. And it's literally just a config file change. So if you've developed your software for Tomahawk 6 with 100 gig, you want to upgrade your network to 200 gig, it's the exact same SDK. That also applies for the CPO, the co-packaged optics version, that it is the exact same silicon, and it's literally just a config file change to say, now I want to use this switch with CPO. This is how I set up my SERDES for that type of connectivity.
This is the first I've seen two words on this slide that you haven't said: training and inference. The data traffic patterns vary enormously in AI throughout the life cycle. Training is the whole different. I mean, I really think of that as probably more of a scale-up problem than a scale-out problem, but also the read versus write and in versus out and all of that sort of thing is just extremely different. And then inference, because of the tremendous amount of experimentation going on right now, particularly in public sector and large enterprise, are you targeting certain customer types, certain use cases here for these? Because I think that as impressive as this is, it's going to have a relatively, while a large total addressable market, a more limited number of scenarios where it's really needed.
I'm not sure about, what we see for Tomahawk 6 is that it bridges scale up and scale out. Inference would normally focus on scale up, but you do see a lot of instances, even with
Inference would be scale up. I would think the other way.
Well, because inference is going to tend to be a smaller number of GPUs or XPUs. So the normal thought was that you could basically do inference on like small number of GPUs, maybe within one rack. We are seeing a lot of cases, however, where that scale up is actually expanded across multiple racks. especially for like mixture of experts, where they're going to have experts. It could be a large number of experts and distributed amongst multiple racks. But I say inference is no longer like 4 GPUs or 8 GPUs or one rack. I mean, there are a lot of cases where we're seeing multiple racks being involved in inference. So those inference workloads do vary fairly dramatically. And that's one of the reasons that we have both Tomahawk 6. So if you wanted to have, we'll get into, we can connect 512 XPUs in a single hop for a scale-up network with Tomahawk 6. Tomahawk 6 also has 200 gig SERDES. So if you had a scale-up network that needed either 200 gig SERDES or that 512 radix, Tomahawk 6 fits into it very well. It doesn't have quite the low latency of a Tomahawk Ultra. So if you're doing inference and that low latency is really important, then Tomahawk Ultra would probably be the better choice for that.
And for training, I would think Ultra would be a better choice because you can really extend training cycles out like, a good deal if you have a latency issue.
Well, I think with with the training, what happens normally is the data transfers tend to be a lot larger. So you don't have as many transactions. The packet sizes are larger. So that flow-through latency, I mean, it's still fairly short latency. It's a pipeline device. It's not, it's quite what we have Tomahawk Ultra. But for the training, first off, you tend to have very large clusters. So you need to have high radix. You need to have, multiple tiers normally. And the Tomahawk Ultra wouldn't have the features to support that because we really wanted to focus on this single hops kind of scale-up connectivity.
All right.
But also, you do find that because, especially on the training side, instead of like these memory transactions that you'll normally have on the scale-up network, it would be large packets, like very large transfers, it'd be megabytes of transfers at a time, and so that instantaneous latency through the device is a little bit less important.
Can you talk a little bit about the power efficiency? I mean, it seems like a lot of these large clusters nowadays, GPUs obviously are consuming a lot of power, but optics and networking and all that's hitting.
Yeah, okay, so let me hop to one slide because I got a lot of content here. I think I've got 8 minutes left, but let me, to address that point, what I'll do is hop to one point here that addresses that. This is one of the, so Tomahawk 6, we discussed, it can handle, it's for like scale up and scale out. On the scale out side, one of the big benefits you're going to get here is that it's very common these days people would have a 200 gig Ethernet connection per XPU. If you wanted to have more bandwidth, you would have multiple rails in parallel. But what you're trying to do is have as wide and flat of a network as possible. There are a lot of issues going to a 3-tier network, and I'll get to that on the next slide. But this is one thing. So Tomahawk 6, we can connect 128K, so it's actually 131,000 XPUs in a 2-tier network. And that 2-tier versus 3-tier might not seem like a big deal, but this is what it boils down to, is that if you have a 2-tier versus a 3-tier, 3-tier will have 2/3 more optics. So that immediately gets to the power efficiency that if you look at the networks today, for the AI clusters, up to 70% of the networking power can be just in the optic. So the fact they have 2/3 more optics with a 3-tier means you're going to wind up with about 2x the power for the network. You'll have higher latency if you have a 3-tier, because now you have potentially 5 hops through the network instead of 3 hops. Higher reliability. So, much fewer switches, less optics. And then one thing that's probably not immediately obvious is that you do get significantly higher performance. And I think there's actually, I'm trying to recall, there's a presentation pretty recently by Microsoft where, which conference it was, within the last month or so. But, what you see is Microsoft, a lot of hyperscalers, a lot of customers are adamant that they don't want to go to more than 2 tiers in the networking, because it makes the congestion control, it makes the load balancing a lot more difficult. So, going to 2-tier versus 3-tier is kind of a big deal, both as far as power efficiency, as far as network efficiency.
So, do you have power specs on each one of these?
We do under NDA. I mean, what I could tell you, it's like much less than 1 watt per gigabit per second. So, but basically,
That's a lot of watts.
yeah, but it's a lot of bandwidth too.
Okay. Yeah.
And
Okay. And do these have the capability to drive either passive or active copper rather than optic?
Yeah. So basically, the SERDES. So the same thing we did with Tomahawk 5, we did with Tomahawk 6. All the SERDES are designed to drive passive copper, to have chip to module for retimed optics, to drive advanced optics like LPO or LRO, and also CPO. So yeah, exact same SERDES can be used for that.
For the scale-up applications, do you see people using lots of copper rather than optic?
Not so much on the scale out. Certainly on the scale up. it's very common these days.
I meant, if I said scale out, I meant scale up.
Yeah.
Within a rack.
Yeah, within a rack, it's all about passive copper connectivity.
Okay.
So that's actually, I think, one big benefit of working with Broadcom is like we're pretty well known to have the best SERDES on the planet. What we could say is that I think I actually have a slide on this. So we just talked about the type of copper type of connectivity. So as we discussed, we got DAC connectivity, pluggable optics, co-packaged optics, 45 plus dB at 200 gig, so insertion loss. Tomahawk 5 generation, we did talk about the fact that we can support like a 4-meter DAC cable from switch to switch. We can't actually say exactly what that meter reach is for 200 gig, because what we're seeing is that all these systems are highly, highly engineered. I'd say that 51.2T kind of Tomahawk 5 generation, basically it was like everyone stamped down a pizza box, it was air-cooled, you had front panel pluggables with a DAC cable. These days, for scale up, everyone's doing these GPU racks where you got your GPU blades on the top and the bottom, you got the networking in the middle, and everything is passively connected. So, and just the different configurations, what they have as far as the number of XPUs, the distances are very different. But this is industry leading as far as like 45 dB plus. So yeah, you can have passive copper connectivity certainly within one rack. I think you go outside of a rack, at that point, you'd probably need to have some kind of active copper, either AEC or ACC or optics.
Okay, thanks.
Okay, so we talked about, I'll just briefly cover, so as far as scale-up connectivity, Tomahawk 6 can support 512 XPUs in a single hop network. So this is more than 7 times the scale of any other competing technology. And again, we see that these scale-up networks, it used to be a couple of years ago, it was maybe 8 GPUs. Today it's like 64 or 72 GPUs in a scale-up network. But we're seeing people definitely want to go to like hundreds, 256, 512. And we've had requests for like 1K or more XPUs and scale up.
So just to be really clear here, when you're talking about connecting these XPUs, let's say you're using Ultra Ethernet, that would be 512 UA link connection.
Well, so UA link is a different standard. So it's basically they use mostly the Ethernet PHY with some modifications. But we believe firmly that Ethernet is the way you should be going for scale up. So UA link is something that we think it's another standard, it's an alternative, but we think there are a lot of benefits to using Ethernet.
Okay.
And then for Ultra Ethernet, there are certain parts of the spec. So the 1.0 spec was kind of here's everything you need for a scale out network. However, there are some technologies in there, in particular with link layer retry, credit-based flow control, that can also be used for scale up. And that's one thing I think Robin will get into is, what is it that differentiates, say, a general data center network versus a scale out versus a scale up network. Okay, we talked about 1 tier. Okay, so as mentioned before, Tomahawk 6 is not just about speeds and feeds. There are a lot of features we have in here that improve the load balancing, the traffic management.
Just for one question.
Sure.
If it's 512 GPUs per Tomahawk 6, what's a 2-tier network look like in this configuration?
So 2-tier would be, normally for a scale-up network, people today are just using single hop, and they're really trying to move, stay within a single hop. They don't want to go to multiple tier. So that would be more on the scale out side. And scale out, what you'd see is that, you see clusters today, maybe tens of thousands of XPUs within a building, maybe going up to 100K, slightly more within a building. After that, you run out of power. So that's why you'd have like a 2-tier scale out network.
You run out of power, not bandwidth.
You run out of power. You can't power the XPUs. They just can't get enough power in one building.
100,000.
From a networking perspective, the single tier is basically switching in the rack. So it's intra-rack communication.
Yep.
Okay. And then so from that jump from a single tier to 2-tier, now we're talking about connecting multiple racks together.
Yep, exactly.
With I'm presuming it's a spine leaf configuration.
Yeah, normally, yeah. So, and usually it's kind of symmetric, full bisectional bandwidth.
Okay. When you hit that, we can't bring enough power limit in.
So
How many racks are we talking about?
Well, so it depends on it depends on the data center configuration, but you can figure that today, what you'll actually see is that for some of the GPU systems that are being deployed, It's not the number of racks because each one of those racks has consumed so much power. So that will actually leave some racks empty. So it's just the total amount of power that goes into the data center that today it's on the order of like tens of thousands, maybe like 30,000, XPUs within a data center. Maybe for these large data centers, getting on the order of like 100,000 XPUs. But after that, literally they just can't supply the power into that building.
And how many XPUs are we talking about per rack?
So today it tends to be on the order of, the high end tends to be like 36 to 72, maybe somewhere in that like tens, like low tens.
Okay.
Certainly less than 100 within a rack.
Okay.
And that's probably where you're going to stay for the foreseeable future. Just the power density within one rack just becomes too high. Okay. One thing quickly I didn't want to talk about is cognitive routing. One thing that's actually created or gotten a lot of attention is this thing we call global load balancing. So the idea here is that with say Tomahawk 2, we start off with dynamic load balancing. And this gets intelligence from a switch. It looks at all the ports, what's the loading on the ports, what is the queue depth for those ports, and then we'll determine what's the best outgoing link based on those local metrics. With global load balancing, we actually get congestion information throughout the network that's fed back from switch to switch, where we can determine the best global path through the network. So that helps out a lot as far as just avoiding long-term congestion, and also as far as avoiding like link failures. So with this global load balancing, for example, we can react to link failures, which become a huge problem with these large clusters, 10,000 times more rapidly than if you had a centralized system with standard Ethernet. So let's see. We do also have a lot of features as far as telemetry and diagnostics. So with our deep insight, we have a lot of features that, again, it's not one size fits all as far as the congestion control that's on the endpoints, the characteristics of the endpoints, the traffic patterns. So there's a lot of telemetry as far as, fast congestion notification that goes back to the sender. CSIG, so this congestion signaling was being standardized within IETF. It's now being standardized within Ultra Ethernet that is supported by Tomahawk 6. And then we have a lot of diagnostics at the physical link layer. So we can actually see if physical links are starting to fail, if they're getting kind of flaky, and then you can proactively replace those links. Yeah, let's see, we talked about that. Okay, so Tomahawk 6 summary. So again, twice the bandwidth of any silicon. So huge benefits as far as the size of the scale-up domain, as far as the fact that you can get to 2 tiers instead of 3 tiers for these very large XPU clusters. And I think we talked about the second point there. So I think one important point is that this is open, this is interoperable. This switch here can work with any endpoint. So, if you have a NIC from different vendors, if you have an embedded Ethernet interface on your XPU, this will work with that. We have a lot of features, a lot of flexibility as far as telemetry, as far as load balancing and congestion control. Overall highest power efficiency, what we've seen is that for the switch systems from previous generations, some of our competitors, just that one system will be 40+% higher power. So, it's not just the fact that we're first to market, but this is actually, by far the most efficient silicon. And also the fact that we have, point solutions for scale up, for scale out, for scale across means we can really optimize the silicon for those use cases.
Which one of these is the 6?
So these are both Tomahawk 6. This has 200 gig SERDES, that has 100 gig SERDES.
Okay, so the 5, 6, bigger 6, little 6.
Yeah.
Okay, thanks.